Alright, instantaneous velocity. This is an important slide to help understand the notation and our eventual formula for instantaneous velocity. We are going to try and answer the velocity question that you see there in the concept box, and in doing so, hopefully make some sense of what this slide is saying. So if you want to pause the video now, read through the slide, and then once you're finished, go ahead and hit continue, and then I have some graphs and some visuals that we're going to work through to hopefully make some sense of what you just read. So go ahead and hit pause right now and read through this this little excerpt on your own. Okay, so the velocity question: a ball rolls a distance of 16 feet in 4 seconds. What is the instantaneous velocity of the ball at a moment of time 3 seconds after it starts to roll? Okay, so I have a picture. You see the red ball up on top of the incline. It has traveled 0 feet, and no seconds have elapsed. All right, so 0 feet and 0 seconds. Now imagine the ball is let go. It runs down the incline, and where you see the open red circle, that's the position of the ball 4 seconds after it has been let go, and it's traveled 16 feet. So we're going to find the velocity average here. So our change in s, or our change in position, how would we find that? Well, it's going to be 16 minus 0. Okay, so here's where it finished. Here's where it started. Take the difference of those, and you find your change in s. Our change in time ends at 4 seconds. Starts at 0, so 4 minus 0. Go ahead and do 16 over 4, and you're going to get 4 feet per second. So the velocity average is 4 feet per second. Now, we're not interested in the velocity average. We're interested in the instantaneous velocity. So here in this diagram, I put a yellow circle at 3 seconds, and we want to find the instantaneous velocity at 3 seconds. So we're going to run into a little bit of an issue using our velocity average formula. So if we try and find our change in t, we are going to be taking 3 and subtracting 3. And in doing so, we are going to be dividing by 0, which we cannot do. All right. Some of you may be tempted to think, oh, well, I'm going to do 3 minus 0. Well, then you would be calculating the average velocity within this interval, and that's not what we want. We want the instantaneous velocity at that point right there. So 3 seconds minus 3 seconds gives us 0. So we cannot be dividing by 0. All right, so what do? What we can do is we can still use our velocity average formula, but we're going to make this, we're going to pick an arbitrary point super close to t equaling 3 seconds. So we're going to make our change in time, the interval, around 3 seconds super close. So in this case, we picked 3.1 seconds. So we're going to do 3.1 minus 3. Okay, and then that's going to give us a change in time of 0.1. Now, the smaller and smaller we make this interval, all right, we're going to be getting a velocity average, but as you can hopefully see, that velocity average becomes a better and better representation of what our instantaneous velocity is going to be. So here, all right, instead of making our interval from 3 to 3.1, it's even smaller. It's 3 to 3.05. So our change in t is would be 3.05 minus 3, which would give us a delta t of 0.05. All right, so the smaller and smaller we can make our interval, our delta t, the better the representation is, or the more better our approximation would be for instantaneous velocity. Now, that only gives us an approximation. All right, so we can use this velocity average over and over and over again and get an approximate answer for instantaneous velocity. But if we want the exact answer, what we're going to need to do is treat it like a limit. All right, and if we find the limit, in this case as t approaches 3, we will have our exact answer. So hopefully this is more clearly summarizes this slide, because now in example 2, we're going to go to example 2 and incorporate some of these concepts. Alright, example 2, a ball rolls down a ramp so that its distance s from the top of the ramp after t seconds is exactly t squared feet. What is the instantaneous velocity after 3 seconds? So I graphed s equaling t squared. And so what did we say what we wanted to do? We're going to use our velocity average formula, but we're going to find what we're going to make our interval, our change in t, super small. So let's stay consistent with what we were doing. Let's say we want our interval to be from 3 to 3.1. Alright, so our velocity average is our change in s over our change in t. So our change in t is going to be 3.1 minus 3. Now, how do we find what our change in s is? So we're going to take this 3.1 and we're going to plug it in for t. So we're going to get 3.1 squared, and then we're going to subtract that, take 3, plug it in for t now, subtract it from 3 squared. So when we go ahead and solve this, we're going to get 0.61 all over 0.1. So it's going to give us 6.1 feet per second. Alright, so that's our average, that's our velocity average. However, it's our average velocity in this interval from here to, let's say, here. Alright, so that velocity average would be a pretty decent approximation for instantaneous velocity at 3 seconds. Okay, so we want to make the approximation even better. Let's take this interval and make it even smaller. Alright, so let's go from 3 to 3.05. Alright, so our change in t is going to be 3.05 minus 3. Our change in s is going to be 3.05 squared minus 3 squared. Alright, that's going to give us 0.3 0.025 over 0.05. Alright, and this is going to be 6.05 feet per second. So this is velocity average, okay, but it can be used as an approximation, a pretty good approximation for our instantaneous velocity at 3 seconds, because it's even closer to t equals 3. Okay, and we can keep doing this and keep doing this, and if we continue the process, we would eventually conclude that the instantaneous velocity is probably around 6 feet per second. Alright, now again, like I said before, this is an approximation. Alright, in order to get the exact answer, what we're going to do is treat it like a limit. So that's what we're going to do right now. We're going to treat this like a limit. Alright, so let me erase this, pause this real quick. Alright, so what we have here and what we're going to solve is the limit as t approaches 3. Alright, so y as t approaches 3. So we want t to be as close to 3 as possible to get our exact answer. So we're going to take the limit of it. So the limit as t approaches 3 of our change in s over our change in t. Alright, so our change in s, so here's our interval. Alright, so from 3 to t, but again, as t is as t approaches 3. So what we're going to do is we're going to take this and plug it into our formula, so or our equation. So we're going to take t and plug it in for t right over here. So you're going to get t squared. And then we're going to subtract, you're going to take 3 and plug it in. So 3 squared. We're going to divide by our delta t, which is going to be t minus 3. Okay, now notice that if we plug in 3 for t right now, we would be dividing by 0. So what we have to do is we have to look to simplify this in a way that we can then plug in 3 for t and not be dividing by 0. Alright, so notice every time I'm going to have to write the limit as t approaches 3. Alright, so I'm going to have t squared minus 9 over t minus 3. I notice the t squared minus 9 is a difference of squares, so that can be factored as t plus 3 times t minus 3 all over t minus 3. The t minus 3's now cancel, so I'm left with the limit as t approaches 3 of t plus 3. Okay, at this point now, I can plug in 3 for t, and we wouldn't be dividing by 0 here. So let's go, 3 plus 3, that's going to give us 6, so 6 feet per second. And so now what we did is we used limits to find our exact answer for instantaneous velocity.